Good morning, everybody, and thanks for coming out this early. So yes, I'll give a brief tutorial on machine learning with Scikit-learn. It's going to be a mixture of slides and notebooks. There's a link down here where you can download both the slides and the notebooks if you want to follow along. So this will start very basic, and then in the end, I'll go to like more advanced and fancy features. I'll not talk about the algorithms themselves very much. I'll talk more about like how to use them with Scikit-learn. So who here has used Scikit-learn in the past? Okay. Who here knows what cross-validation is? Who here knows what machine learning is? Okay, same people. That's good. So I'll give a very brief introduction to machine learning, as most of you know this, and then we're going to go into Scikit-learn more. To start off, a little bit about myself. I did my PhD in Germany at the University of Bonn in computer vision and machine learning. I went to Amazon Machine Learning in Berlin for about a year. And now, since the last year, I'm at the NYU Center for Data Science. So I think since my PhD days, I've been a contributor to Scikit-learn. And now I'm lucky that I can do this full time. So NYU pays me to work on Scikit-learn nearly all of my time. So what is Scikit-learn? So Scikit-learn is a library to do machine learning, and comes with, obviously, it's a Python library. This is PyData. And so it's a library, which means you have to write code. So it gives you a lot of function and classes to write all kinds of classification, regression, clustering algorithms, but also tools to help you apply these algorithms, doing feature selection, feature extraction, doing parameter estimation, evaluation, and so on. So it's a whole set of algorithms together with tools to apply these algorithms on your data and evaluate them. So I'm one of the core devs, and me together with Olivier Grisel, we do the releases. But Scikit-learn is really a huge community project. So here are, I think, there are currently about 30 core developers that can commit to the repository. But each release is made up of like 100 to 200 people contributing in varying degrees. And we really much welcome all contributions. And you don't need to be a machine learning expert to contribute. So yeah, so I'll do some notebooks interactively. Here's the link again, bit.ly/skl-osdc, because I didn't want to do two links for the same week. So OSDC is on Friday. Best resource for Scikit-learn is definitely the website. So in addition to everything I talk about, you should check out the user guide. It's very in-depth. It covers much more than I could cover in 1.5 hours. So definitely go to the website. So here I have the 1.16 documentation. Current version is actually 1.17 that released last Thursday. And so the user guide, the quick start guide, and the API documentations are your friend. Check them out, definitely. So what is machine learning? So my favorite example, and one of the most classical examples of machine learning, is spam classification. So everybody of us gets a lot of emails every day, and you definitely want not to read all of them. So you want your email client to distinguish the ones that you want to read, the ham, from the ones that you don't want to read, the spam. And you want to do the email client is supposed to do this automatically. And the way that all modern email clients do this is by learning from data. So they look at a lot of emails that they know are good. They look at a lot of emails that are marked as spam by you or by someone else. And then they learn the model of what it means for an email to be spam or not spam. And this is sort of the essence of machine learning, is learn from annotated data where you know what the desired output is and predict this on new data. So if you get a new email, your email program can use the model it built of what a spam email looks like and decide if a new email is spam or not. So this is the main paradigm of supervised learning. So as I said, you start off with some training labels and some training data. So your data could be a huge corpus of emails, and training labels be are they spam or not. And you use these together to build the machine learning model. Then incoming new emails are your test data, and you can use your model to make a prediction. Usually you will also, once you build the model, you want to evaluate how well does this model work on your data. So you don't want to just use a model. You want to know that you can trust the model. So often we use additional test labels, additional annotations to evaluate how well did our model do. And if the evaluation is good, then we can put it into production. So I'll mostly talk about supervised machine learning, which is of this kind today. And there's really two phases in supervised machine learning. One is called training, where you build your model, and one that's called generalization, where you try to apply your model to new data that it hasn't seen before. Oh, by the way, I have a tendency to go way too fast. Please interrupt me or regularly tell me to go slower if I'm going too fast. Probably not yet, but soon. So how does this look like in Scikit-learn? So the Scikit-learn API is quite simple, and it tries to mirror this process of building the model and then applying it. So first you have to pick what kind of classification algorithm you want to use. For example, for the email data. So let's say you want to use a random forest classifier. And let's not worry about what this does for the moment. The first step is to import it and then instantiate the model. So CLF is now an instance of the random forest classifier. This object encapsulates the algorithm to build the model and will also store everything that we learned from the data. We call all models in Scikit-learn have a fit function. The fit function builds the model. And in supervised learning, it gets the training data, which we call xtrain, and the training labels, which is the annotation, the desired output, ytrain. This builds the random forest model, which is like an ensemble of trees. And all these trees get stored in a CLF class, or in a CLF object. Then we can apply this model, this random forest model, to new data. Let's say it's called xtest, and call the predict function. And the predict function will tell us what the model thinks, what the labels should be. What should be the output that we called y for this new test data. And then, if we want to evaluate our model, we can use the score function. The score function basically makes the prediction same as predict, but then it compares the prediction to the true outcome that we know, y-test. Y-test is the known true outcome for x-test. And this will tell us whether our model is any good or not. So let's see how this looks like in practice. So I'm switching over to the notebooks, the Jupyter notebook. This is part 1, Intro to Scikit-learn. So before we can do any machine learning, we need to have some data to do machine learning with. I'll use one of the toy data sets that ships with Scikit-learn, the digits data set. You can load this with the load digits function, which will give you this digit object, which is something like a dictionary. It's a bunch, but think of it as a dictionary. It has these keys here: images, description, target names, and data. So the important ones for us are image, target, and data. So the images are a NumPy array. Everything that Scikit-learn works on basically is NumPy arrays. Always think in NumPy arrays. And here these digits are 1800 times 8 times 8 array. So this is 1800 rows, and each of them is an 8 times 8 array. And the first array looks something like this. And maybe it's not very clear what this represents, but we can use matplotlib to plot this, and we can see, well, this is a very, very low resolution handwritten 0. So it's an 8 times 8 pixel grayscale image. And the task here is to classify this image into which digit it is. So this is a classification task with 10 classes, the digits from 0 to 9. The input are these 64 pixels, 64 grayscale values. So we can reshape this. This is what's stored in digits.data. This is just each row in this NumPy array is one of the digits flattened out. So this is just the 64 grayscale values in one row. And the targets are one number for each of the 1800 images. And these are like the numbers 0 to 9. You can see the first target is 0 because the image is of a handwritten 0. And what's really important to note here is that the data is always a NumPy array, or SciPy sparse matrix, that is number of samples times number of features. So each row is one example, and each column is one feature. Here, a feature is, for example, the top left pixel. And you always need to make your data to be in this form. And also, basically, For most of scikit-learn, it needs to be numeric data, like float data. But I'll talk a little bit more about this later. So once you have your data in this format, you can then do machine learning with it. So we said we need to have a training set to build the model, and a test set to evaluate how well our model does, so we know whether it's any good. There's a function in scikit-learn that does this for you, the train test split function. What this does is basically it just shuffles your data randomly and then splits off 25% of both the data and the labels as a test set. So now I have train x test, so x is always the data, and y train, y test. This is the desired output, which are these labels 0 to 9. And now we can apply any of the many machine learning algorithms in scikit-learn. For example, let's choose a linear SVM, which is called linear SVC for support vector classifier in scikit-learn. So the first thing we need to do is to instantiate the class to get an SVM object. This is also the moment when we can set some parameters. I'll talk more about setting parameters later. But basically, all machine learning models have a lot of parameters that you somehow need to tune. And this is the moment when you can set them. Then you call the fit function with the training data, numpy array, number samples, number features, and the training labels. So this built the model. In this case, it estimated the coefficients of this linear classifier and stored them in the SVM object. Now we can apply our model. So here, first, I call the predict function on the training data to get a baseline on what it's doing. So you see that it returns a 1D numpy array with numbers from, well, you don't see it, but numbers from 0 to 9. And you can compare this like just visually with the true desired output y train, and you see they're the same. That's not very surprising, as this is the data it was trained with. We can also call the score function. The score function computes how many of these numbers in the top and the bottom row are exactly the same, and it says 99.5% of these numbers are the same. So for 99.5% of the training data, we made the right prediction. That's not really interesting because we could just learn it by heart. The interesting part is this. So we can also apply the model to our test set that it didn't see before. So these are new digits that were not used to build the model. And here we perform at 95.3%. So we made the right prediction for going from the image to the actual number as written in 95% of the cases, which is pretty good for a 10-class classification task. So this is a very simple toy data set. So this doesn't mean a lot, but it's more about seeing what is the process. So the process is we import the model, we instantiate it, we fit it with our training data, and then we can call predict to make predictions or score to evaluate the model. Any questions so far?
Instead of passing a single float, you pass an array of floats, an array of...
You mean as a parameter?
Yeah, to search on the grid.
I'll tell you how to do grid search later. This is not how you do it. OK, and one of the nice things about scikit-learn is that you can do this. It looks the same for all models. The parameters are different, but the interface is exactly the same. So instead of using a linear SVM, you can, for example, use a random forest classifier. And so we import the random forest classifier. We set some parameters. We call a fit function and a score function. And so this built the random forest model, stored in the RF object, and we can apply it to the test data and see we did 98% correct. So, and we can do this with a whole bunch of models if you want. I mean, one might argue it's better to understand your data first, but if you want, you can apply a whole array of machine learning algorithms in scikit-learn. And this is actually what I'm going to demonstrate now. This is an example from GitHub. It's called classifier comparison. And so I don't want to go through the details. The main takeaway here is we make a list of classifiers here. So these are like not all of, by far not all of them, but just some of the like interesting classifiers in scikit-learn. And then we make like 3 data sets. The moons make circles and linear separable. And then for each combination of data set, we fit it, and then we score it. And the rest is just plotting code. So basically, we can just iterate over all models and try and see what they do. And what we get out is this. But it's too small. Let's see. So here, you can see on the very left, you can see the 3 data sets. These are all 2-class binary classification data sets in 2D. So one features on the x-axis, the other features on the y-axis. Each dot represents a data point, and there's a blue class and a red class. And then you can see how all of these different models perform. So, sorry. So the red area here is always what the model thinks where the red class is, and the blue area is where it thinks that a blue class is. And there are some degrees of uncertainty. And so you can look at these and try to understand different models. But the main message is really, you can just loop over these things and look at what they do. And it's a very consistent interface. And so you can do many different things. And replacing one model by a different one is very easy. Okay. Any questions? OK. So the other big kind of machine learning algorithms is unsupervised machine learning algorithms. I'm not going to talk about it that much, but I definitely want to talk about it shortly. So in unsupervised machine learning, there's many different flavors, but all of them have in common that someone just hands you a chunk of data and says, this is your data, do something with it. And usually the idea is to learn something about your data, often in an exploratory fashion, or to compress your data, or find a new representation. So these class of algorithms are like clustering, dimensionality reduction, manifold learning, matrix decomposition, and so on. And so you just get your training data, and you build a model from it. And often that's it. Sometimes you can also use this model, apply it to test data, and get a new view of your data. This is often the case for things like PCA, dimensionality reduction, NMF, and so on. And this is how it looks like in Scikit-learn. So it's very simple, similar. So PCA is principal component analysis that I don't have time to explain. But the idea is, again, you instantiate your model. You fit your model with the data. This time, there's only X train. There's no Y train. Because this is an unsupervised model, we only have data. There's no desired outcome. This builds a model stored in PCA. And then we can use the transform method to transform either the training data or some new test data to a new representation. This is true for all what I call unsupervised transformations, which take one view of the data and create a new view. And so I want to give some examples of this now. So here at the beginning, I just import some stuff, load the digits that I showed in the last notebook, and split it into a training and a test set. Arguably, the simplest form of unsupervised learning, maybe not even unsupervised learning, is just preprocessing your data by removing the mean and rescaling to unit variance. The reason why you might want to do this is because many of the models in Scikit-learn behave much better if you do this preprocessing. For some, it doesn't matter, but for some, it's good to do this. So it's an application I think I want to demonstrate. So again, you import the model. So here it's the standard scaler, which literally just subtracts the mean and then scales by the standard deviation. You import it, you instantiate the model, and you fit it using the training data. And then you can transform the training data. So these are really, there's 3 important methods in Scikit-learn: fit, predict, and transform. Predict is to predict desired output, a target that we call Y usually. And transform is to get a new free view, a new representation of the data that we also usually call X again. So here I call it scalar transform and get X train scaled out. So X train, as you might remember, here is the subset of the digits. It's 1,300 digits, 64-dimensional. After we scaled it, obviously it's the same shape, only now the mean is 0, and the standard deviation is 1. There's some zeros in there. That's because some of the pixels have no variation. They're always white. And then we can use the transform method also to transform the test portion of the data. So something that you should note here is the test data is not, the transform test data is not zero mean. So the whole idea why we want to do this in Scikit-learn and not do it yourself is you want to subtract the mean of the training data and divide by the standard deviation of the training data, even on a test data. It's important that you apply the same transformations, the same pre-processing steps to your training and your test data so that your machine learning algorithms can work. So that means that if you transform your test data, it's not necessarily going to be zero mean. Questions? The question is there a method to do the inverse of the transformation? And the answer is yes, it's called inverse transform. Not all methods, not all transformations have that. The ones where you expect it to work have it. So sometimes it might not be super non-trivial, but like all of the scaling, the principal component analysis, the matrix decomposition, they all have this inverse transform. Any other questions? Okay. So the next thing I wanted to demo is like something slightly more interesting in terms of unsupervised learning. It's principal component analysis. So maybe the two-sentence summary, or one of the possible two-sentence summaries for the people who don't know it. This is something that basically models your data as a big Gaussian blob, and then it tries to find the main axis of this Gaussian blob, where the variance is the largest. So it tries to find the directions in which the data varies most. So it tries to find the first direction, which the data varies most. Then it tries to find an orthogonal direction, which is the next direction of maximum variance, and so on. And it's often used to project your data down to reduce the dimensionality. So here we start with a 64-dimensional digits data set. And this is, you can look at each individual image quite easily. It's like it's an 8x8 image. But if you want to look at many of the data points together, it's really hard because it's a 64-dimensional space. And your screen is only 2-dimensional. So we might want to try to project down the 64-dimensional space to, say, a 2-dimensional space to look at it. And PCA is basically the simplest method to do this. So again, we call the fit function here with the training data xtrain. And no target y. And if you transform the training data, you see that it went from being 64-dimensional to 2-dimensional. And now we can easily visualize it. So here I plotted the first principal component on the x-axis, the second, principal component on the y-axis, and I actually colored the data, so the data points by the class label. So the PCA is completely unsupervised. Just so that you see what's going on in this visualization, I choose the color of each data point based on which of the 10 digits it is. And so, without going really into PCA, it's a bit hard to understand what the two axes mean. But often it's illustrative to look at this low-dimensional representation. And you can see, for example, that even in this kind of unsupervised method, the blue points are very far from the other points. And which is probably the 0 or the 1. And teal points and the yellow points are kind of similar, but not that similar. And there's a lot of classes that are all bunched up together, which is probably like 4 and 7 and so on. So you can see at least some of the classes are very separated already. If,
Yeah, it definitely separates classes. Also, regionally, there's a lot of overlap. And if you were using, what would you use the PCA for? Is this would be a final result, I imagine? Might you use a larger number of dimensions to use as a classifier, or what would be the goal?
so you wouldn't go down to 2 dimensions if your goal is to visualize, because here, yeah, some of the points you can clearly not distinguish anymore, like the red and the orange or something, they completely overlap. But you could go to more dimensions. Often, I would actually not use PCA and then do classification. Often it's better to do classification on the original data space, but it depends on your data. For example, for face recognition, for a long time before neural nets became popular, people used just PCA on face images and then ran a classifier on the PCA transformed version. So sometimes it's good to reduce the dimensionality. It can also be a way to make the computation cheaper. If you have, I don't know, a 10,000 dimensional dense feature space, it might be very expensive to learn a classifier on it. Depending on your classifier, it might be cheaper to do a PCA first. But by default, I wouldn't use this as a pre-processing method. Sometimes it might make sense, but I wouldn't suggest it as a general mechanism. Other questions? OK. So to summarize the basic API of Scikit-learn, so all of the machine learning models are implemented in classes, which we in general call estimators. And they all have a fit method. The unsupervised models get only the data x, and supervised models get the data x and some desired output y, which could be a continuous regression value or a discrete classification task. And if you want to predict, again, something like a y, a one-dimensional thing, then you can use the predict method. So that's for classification, regression, and also clustering. And if you want to transform your data into a new representation, use the transform method. So this is for pre-processing, like the scaling of the data, for dimensionality reduction, as we saw with the PCA, for selecting features, or for extracting features. And we'll see a little bit more what these could be later. Any questions about API? No. OK. So, OK. You all know about cross-validation, apparently, so I'm going to go through this relatively quickly. So until now, I said you have all your data. You build your model on the training part, and then you evaluate on the test part. That's sort of a good baseline, but there's cross-validation, which is the way people usually evaluate their model, which is you split your data into many parts, say 5 parts. Then you leave out the first part, called fold, as a test data, and train your model on fold 2, 3, 4, and 5. This gives you one evaluation of the model, one score. Then you throw this model away, and you build a new model. This time, you use fold 2 as a test data, and the rest as the training data. This gives you another scoring, another evaluation of how well your model generalizes to new data. In this case, how well it generalizes to fold 2. And you keep on doing this. The benefit of doing this cross-validation scheme, well, there's 2 main benefits. One is every data point was in a test set exactly once. So if you just do a single split, it could be that you had bad luck and chose a very hard test set, or you chose a very easy test set just by chance. And so this might not represent well how well your model generalizes once it actually goes to production. If you do cross-validation, each data point will be in the test set once, so you're kind of protected against this. Also, instead of having a single score on the test set, you now have 5 scores, which means you have some estimate of the variance between the scores. So if one of them is like 10% accuracy and one of them is 90% accuracy, well, then I wouldn't trust the model, because you have no idea what it's actually going to do. But if they're fairly close together, you can be sure that the model is pretty consistent. So, OK, so how do we do this with Scikit-learn? Oh, maybe one aside. when I say cross-validation, I'm really talking about just evaluating a model. So I have one set of model parameters, and I want to say, how good is this model? Then I do cross-validation, and it gives me back 5 numbers, and then I can look at average, standard deviation, or whatever statistics I want of these 5 numbers. This is what I mean by cross-validation. No, sorry. So I load my digits data set again. And the way to do cross-validation in Scikit-learn, at least the easiest way, is to use the cross-val score function from the cross-validation module. And so let's say I want to evaluate a linear SVM model on the digits data. Then I use the cross-val score function. I gave it an instance of the classifier I want to evaluate, the linear SVC, the data X, and the labels Y. So this is the whole data set and the whole set of labels. And then I can specify the way in which it will do cross-validation. Here I say CV equal to 5, which means it will do 5-fold cross-validation. It'll give me back 5 scores, which are the accuracy on this of the 5 different models that are trained. I can do CV equal to 10, and then I will do 10-fold cross-validation. So actually, by default, Scikit-learn does something a bit more advanced than cross-validation. If you do classification, so it detects if your model is a classifier and then does stratified cross-validation. Stratified cross-validation means that it makes sure that the fractions or the ratios of the classes in each fold reflect the ratio of the classes overall. Often you have like one class being a lot more frequent than the other class. Let's say you have person clicks on an ad or person doesn't click on an ad. Nobody ever clicks on ad, so you will have a lot of data that does not click and very little data that is click. And so if you're unlucky and you just split your data in some way, it could be that you have no click in your training data or that you have no click in your test data. Then your evaluation will be meaningless. If you do stratified cross-validation, you make sure that in each fold, the ratio of click to non-click is the same as in the overall data set. So you make sure you have something of everything in each fold and that they represent the overall statistics. And that's what's happening here by default. Okay, so much about like what the cross-validation does. There's, you can also, wait, do I have it here? No, yeah, later. You can also change the metric that is used. So by default, classifiers are evaluated with the accuracy metric, which just says what percentage of the data points were classified correctly. Again, if you say, go to the very imbalanced click-non-click example, if you say, oh, users never click, I just predict constant never click, you will be 99.9% correct, because 99.9% or something like that is no click. So even though you're 99.9% correct, you can just do constant predictions. So accuracy is not very good in unbalanced settings. And you can maybe try to use a different scoring function, like here I use F1 macro, which is the macro average F1 score. There's other scores that I like to do. So here, just to have an example of a binary classification task, for a second, I classify even versus uneven digits. So I do y modulo 2. So it's 0 if it was an even digit, 1 if it was an uneven digit. Not a very sensible task, but just as an example. For binary tasks, we also have average precision and the area under the ROC curve. And these two are also much better for imbalanced classes. And so if you have imbalanced binary classification, I would very much suggest that you use something like the ROC AOC or average precision to do your evaluation. And there's many more. There's many regression metrics. There's also metrics for clustering and so on. So I also already said it doesn't do standard cross-validation by default, but there's like a whole range of different things different ways how you can do cross-validation. And I just want to highlight one of them. So if you look in the documentation in the cross-validation module, you'll now find like 10 or 15 ways of how to split your data. And I just wanted to give one more example, which is the shuffle split cross-validation. And it does what it says. It shuffles your data and then splits off a given percentage of your data. So here, I say, this is the length of my data. So this is the number of data points I have. I want to do 10 repetitions, and I want 40% of my data in the test set. And then it will shuffle and split my data 10 times into 40/60. And sometimes you might want to do this because it allows you to control the number of repetitions independently of how large the test set is. So this might be good for very small test sets sometimes. But yeah, as I said, there's many other different ways to do cross-validation that you can specify by giving a CV option here. You can also, if you want, there's an n jobs option, which allows you to do this in parallel over multiple cores. Any questions about cross-validation? OK. So, as I already said, until now I said, this is how machine learning works. You essentially do model, you call fit, and you call predict. And if that was all it is to machine learning, our lives would be much easier. Unfortunately, most of the models have a whole swath of different parameters that you want to adjust. And the tool of choice to adjust them is grid search. The way I like to do grid search is I split my data into a training set and a test set. Then I do cross-validation on the training set to find the right parameters. And then I do a final evaluation on the test set. The way I do it like this is that if you try a whole lot of different parameters, it might be possible that you overfit the parameters that you try out to your data set. So here, I find the parameters on the training part using cross-validation. And then I do a final evaluation on a test set, which I didn't touch before at all. So you should only run something on a test set exactly once. And if you do it only exactly once, you will have an unbiased estimate of how well you would do on new unseen data, aka in production. If you use your test set multiple times, you make a multiple hypothesis testing error, basically, and you can overfit. And then sort of what you do in the cross-validation is that for each split of the cross-validation, you start out with some parameter setting. Like for the support vector machine, you have the parameters C and gamma, and you start varying C, and you start varying gamma, and then you have all possible combinations of the two, and you wait a very long time until you tried out all of them. And for each of them, you run a cross-validation like 5-fold or 10-fold. And then you pick the best one. Oops. So let's see how the code looks for this. So grid search is implemented, or grid search with cross-validation is implemented in grid search CV, which is, again, a class. And here I'm going to give the example of doing grid search on the two hyperparameters of the support vector classifier as the standard kernel SVM. I split my data into a training and a test part. I'll adjust the parameters on a training part, evaluate it on a test part. I need to define the parameters I want to search over. So as I said, there's C and gamma for the kernel support vector machine with RBF kernel. And the way I declare the parameters I want to search over is as a dictionary. The keys in the dictionary are the names of the parameters, and the values are the values I want to try out. So here I used like an exponential scaling of both the gamma and the C parameter. And hopefully, like in the next version, we'll have a dictionary that tells you all the right values to search over. Currently, this is sort of expert knowledge on what you want to search over. And what a grid search will do, it will try all possible combinations of these. And I didn't run the first cell. Then you can instantiate the grid search CV object with the support vector classifier, your grid of parameters, and I also tell it to be verbose so we see what's happening here. And this grid search CV object is what we call a meta estimator. This means it gets an estimator, in this case a support vector machine, and creates a new model from it. And as you can see here in the following lines, this grid search object behaves exactly like any other classifier would do. It has a fit, a predict, and a score method. Only it does like a whole lot of things in these methods, in particular in fit. So if I call fit on the training data and training labels, it will run cross-validation. By default, it does threefold cross-validation. And you can see it tries the first set of parameters here, this gamma and this C value, and scores the model. Then it does, again, the gamma and the C value on the second split of the threefold cross-validation and the third split of the threefold cross-validation. Then it goes to the next set of parameters and the next set of parameters and so on. So it tries out all these different set of parameters. And then in the end, it finds the best one. Once it picked, let me finish. Once it picked the best set of parameters, it stores these parameters. It retrains the model on the whole training set and stores this model. If I call predict on the test set, it will use the model with the best parameters as found by cross-validation, trained on the whole training set. There was a question?
Doing cross-validation on the X-train as well. Do the scoring.
Sorry, I'm not sure I understand. So it does cross-validation on X-train, Y-train. I only passed it X-train, Y-train, right? So this is what it uses for cross-validation. So it splits up X-train and Y-train. So this is the image. So it splits up the training set. And I don't touch the test set at all here. OK, cool. So what it does for you is, not only does it do a grid search, but it retrains the model afterwards on the whole training set. And then if I do predict, it'll use the best model I was found, retrained on the whole data set. And this makes it very easy to do the thing that I recommended before. So now I can just call score on a test set, and this will give me like an independent estimate of how well my model will generalize. And here it's 99.1%, which is pretty good. If you want, you can also inspect what parameters you looked at. You don't actually need to do this if you want to do predictions, but you can inspect it. It's often good to see if they are on the borders of what you searched over. If they are, you might want to extend your search range. You can also visualize what the scores were for each different fold. At the moment, it's a bit tricky. It'll become easier in the next release. But here, I look at the grid scores. The grid scores attribute of grid search stores all of the numbers that were outputted here. So all the scores for all splits for all parameter settings. And I extract them. I get here the 1, which is the mean cross-validation score. I had 6 different values for C and 5 different values for gamma. I reshaped the array. And this is a heat map of the accuracy as a function of the C and gamma parameters. So this is the cross-validation accuracy, not the tested accuracy. And so, sorry for Jet. So the dark red is good. It's the high 90s. The blue is 10%, which is basically chance performance. You see that actually the kernel SVM is very, very sensitive to the setting of the parameters. But sort of there's a decent range here where it's working very well. Outside of this, it's not working at all, basically. Sorry, can you speak up a bit? Not sure. So, well, if you have a string parameter, you can just do if you have a string parameter, you can just do this. If you have conditional parameters, so let's say you want to search over a linear in the RBF kernel, one thing you could do is you can pass a list of dicts. So you can do something like what did I press? Oh no, I pressed insert. Don't you hate it when you press insert? I have no idea where it is on this keyboard. Seriously though. Oh no, I didn't. So you can do kernel equal to, kernel is RBF. So this is the first entry in a list, and then I can do a second dictionary where kernel is linear, and then I only search over C, for example. Yes? Yes. So very good question. I forgot to mention that. So this has a whole lot of parameters. The important ones are CV, so you can use the whole range of different cross-validation strategies, or you can do 5-fold or 10-fold. So by default, that's 3-fold stratified. Now I do 5-fold stratified, and you do scoring equal to AUC. So that wouldn't work because it's not a binary task. But you can do scoring equal to any of the many scoring methods, and you can do n jobs equal to -1 to use all of your cores. So these are like how you can customize this scoring and CV. More questions? No. OK. I think the optimum is here. I mean, but I don't expect it to vary very much here. So this is all the same for this. You can try if you want. Yeah, if it was here, I would extend it. Or if it was here, I would extend it. But I'm pretty sure it seems fine to me here. OK. So the other line that I did so far is I said, well, you take your training data and your training labels and you put it into your model. Only that never happens. Usually, you have a whole lot of different steps from when someone gives you your data until you can build your model. For example, you might have feature extraction from dictionaries or text or images or whatever. You might have scaling, preprocessing, normalization, and you might do feature selection. And if you have all these steps, a common mistake that people do is they preprocess all their data, and then they do cross-validation just on their classifier. That's really, really problematic, because if you do this, then the test fold in your cross-validation was already seen in the scaling, in the feature extraction, in the feature selection. And so your cross-validation doesn't give you an unbiased estimate of how well you generalize. It's really important that you do cross-validation over all the steps in your pipelines, over everything you do, so that you never leak any information from the test folds into your process. This is also called contamination in statistics, I think, if you leak information. And so we want to avoid this by doing cross-validation over the whole pipeline. And the way to do this in Scikit-learn is using pipelines. So pipelines are a slightly more advanced concept, but I realized way too few people use them, and you should all be using them. If you're not using them, you're doing it wrong. You should learn how they work. And I hope I'll be able to explain it to you. So actually, this presentation doesn't have the image. No. So I start off with the boring digits data set. And let's say we want to scale our data to have 0 mean unit variance before we apply our SVM. The way we can do this with using pipelines is we create a new object using the pipeline class, which will be, again, a meta estimator. And we give it 2 steps. Actually, let me use the new instance. So there's the verbose version and the less verbose version. I like the less verbose version better. And I should run all my cells. And I should import what I use. So I give 2 steps here, the standard scalar and the SVM. In a pipeline, all steps but the last needs to be transformers. So they need to have a transform method. And what will happen here is equivalent to making a standard scalar, doing fit on the training set, scaling the training set, xtrain scale is scalar dot transform xtrain, and then SVM is svc dot fit xtrain scaled ytrain. So this is what happens in the pipeline.fit. It takes the first step, which is standard scalar. It calls fit on the first step. Then it calls transform on the first step, which gives out a transformed version. Then it calls fit on the next step. If the next step is again a transformer, it will call transform again. Here there's only 2 steps, and so it'll just call fit. That's what happens in fit. What happens in predict or in score is just you get your test data. It'll call transform on the first step, pass the transform version to the second step. If it's a transformer, again do transform, and then in the end do score or predict. So I won't write out what this code does here, just does the transform and so on. But you can see that. So this is a very common pattern that you fit something, transform, then give the output to something else. And you can shorten this code a lot and get rid of a lot of bugs if you just use the pipeline instead. So it just makes your code shorter. But what it also enables, so this is now the SVM trained and predicted on the scaled data set. What it also allows you is to use this whole pipeline now in cross-validation. So because this pipeline object is one estimator, I can give this pipeline to cross-val score. And if I do this, it will run cross-validation over the whole pipeline. So for each of the 3 splits, it will find the mean of the 2 training splits and the standard deviation of the 2 training splits, scales the 2 training splits, pass them to the SVM, train the SVM. Then use the mean and standard deviation of the 2 training splits, apply them to the test split, and score on the SVM. So this is like a really important concept. And so if you would just scale your data beforehand, the standard scalar on X, and then transformed all of X, you would have used information, namely the mean and standard deviation of the test fold. And that is leaking information. It might not be that bad for the scaling, but sort of if you do more advanced things, if you do things, or if you have less data, it might really make a difference. You should never use any of your information about your test data, not even what the mean and standard deviation is. Any questions about what happens here?
So main pipeline takes any number of transformations and some classifier?
Yes, any number of transformations, and the last one is arbitrary. If the last one is a transformer, the pipeline will have a transform method. If the last one is a classifier or a regressor, it'll have a predict and a score. So the whole thing acts the same as the last part.
Is there a way to calibrate it using random data?
Sorry, how do you mean?
Calibrate against using random data. So we built a train the model using our test data, run it against some random data to see if
I have not really heard about this process. Dummy classifier does a baseline what a random classifier does. I mean, it's kind of similar. it gives you a baseline on what the stupidest thing could be. But actually, I would argue that, I mean, it's good to try this out, but I would argue that if you should use a different metric so that you know what chance means. If you use accuracy on an imbalanced data set, chance performance can be 99.9%, as I said before. So maybe this is not a good method because you need to make in your head some weird transition of what 99% means. You should rather use a metric where you know what is chance performance in this metric, like AUC. So that would be more my advice. It's good to know what like random performance is on your data, and you can do that, but I would rather use a different metric usually. Okay, other questions? Okay, so you can also use grid search with a pipeline, and that's actually like the main application of pipelines, or one of the main applications of pipelines. And it works the same as before, with a slight caveat that is, and I need to change this, that you need to say which step in the pipeline do you want to change the parameter at. So each step in the pipeline has a name. And if you use the verbose version, you gave it a name. If you use a short version, it will just use the lowercase class name, as you can see here. So here there's two steps. The first step is standard scalar. The second step is called SVC. These are just string names. And so I want to adjust the parameters of the SVC, of the support vector classifier. And so I have to say, the parameters I want to adjust are SVC double underscore, and then the parameter I want to adjust, for example, so C and gamma. So this is a double underscore, which is like a special syntax in Scikit-learn, and says in the grid search, in the pipeline step SVC, I want to adjust the parameter C. And then I can instantiate the pipeline, give it the pipeline object, give it the parameter grid, and call fit and score as I did before. And now at each step, it will learn how to find mean, standard deviation, and so for each different parameter setting, it'll find mean and standard deviation, and then try the parameter settings and so on. Questions? Yes, definitely. So you can also do like, I'm sorry, I don't have an example of this thing, but you could do like standard scalar. Or maybe I have an example of this on the next notebook. So if you want to adjust whether the standard scalar subtracts the mean or not, it would be like this. No, actually, I'm going to have an example of this later, hopefully. Or any other questions? No. Yes. Do cross-validation overall steps jointly. Keep a separate test set until the very end. I'm not going to let you repeat this, but repeat it in your head. So now I want to talk a little bit more about applications, in particular working with text data. Who here works with text data? That's not that many people. Wow. Who here knows what a bag of words representation is? All right. So I very briefly want to go over the bag of words representation and then see how to do it in Scikit-learn. So the bag of words representation is a way to go from free text strings to a numeric representation that machine learning algorithms can work with. So a string might look like this. So one of your data points might be a string, like this is how you get ants. Or it might be a Yelp review, or it might be a book by Shakespeare. And the way to get this into a numeric representation that is fixed length is First, you tokenize this, which is basically split it up into words. For example, by white space. We just use simple regex for this in Scikit-learn, but you can get much more advanced if you like. We also lowercase everything to normalize this. Then we build the vocabulary over all the documents, so like all the Yelp reviews in your data set. Then you have a huge vocabulary going from aardvark to 6. Finally, you go back to your initial data point that you want to encode, and you build a large sparse matrix encoding. For each word in your vocabulary, you count how often does this word appear in this data point. So aardvark doesn't appear at all, so you write a 0. A lot of other words don't appear at all. But ants appear, so you write a 1 there. And for all of the words that appear, you write a 1. So you have a very long vector, usually tens of thousands of hundreds of thousands of entries, with very few ones and a lot of zeros. And so you want to represent this as a sparse matrix, which only stores the points that are non-zero. And so these steps are implemented in the count vectorizer, and a slightly rescaled version of this in the TF-IDF vectorizer. So I'm going to do my favorite non-politically correct application, which is insult detection, which is was a Kaggle competition I did I don't know how many years ago. So this is about social commentary on the internet. And so on the internet, there's people who make very good points, like, I really don't understand your point. It seems like that you're mixing apples and oranges. And then, as on YouTube, someone replies, clearly you're a fucktard. So this is the kind of text we want to work with here, and we want to say, which of these are people arguing, and which of these are people insulting each other personally, and you want to block the insults. Oh, if you're offended by swear words, close your eyes now. Close your eyes before I did that. Wow, this is... No! What happened? I don't know what happened. OK, cool. So as always, I have all the data in a CSV file, and I use pandas for the only thing I ever use it for, which is reading CSV files. It's not true. It's the thing I mostly use it for. Yeah, so this is your data. It's very nice. It has a binary insult or not, a date that we're going to ignore, and then a wonderful string of very polite people. So we're going to, it's actually not really necessary, but we're going to make the insult column a NumPy array, which is now just ones and zeros. NumPy array, no metadata anymore. And we're going to get the command column out and just make it a list. So this is just a list of strings now. So we have an array of 0 and 1s and a list of strings. And here's like one of the data points, year and where are you now. If you want, you can look at the zeros data point, but maybe not. I also load the test data with pandas and do the same thing. Get the insult column out and get the text out. Yeah. So when I wrote this, the pandas support in Scikit-learn wasn't that great. Since then, I fixed it. And now you can also pass series and data frames and stuff if you want. So we're going to use the count vectorizer to transform the strings into sparse matrices. So I instantiate the count vectorizer. I call fit. So count vectorizer is a transformer. So I can use transform to process my data. I can also introspect it, look at the vocabulary. So this is a very small data set. Did I show how large it is? Pandas shows me probably how large it is. Yeah, so there's like 4,000 points in the training set. And there's in total 60,500 words. So some of them are numbers or special characters or something, but that's the size of the vocabulary. And here you can see what it is. Great. There's many words in this vocabulary. Then we can use the transform method. And this will give me an encoding. So again, rows are samples. So I have, again, like about 4,000 different training data points. And I have one feature per word or per token, which is 16,500. So we can look again at a single data point. So here's, yeah, where are you now? And if you look at the entries in the row of the sparse matrix, you can see that there's something like there's non-zero entry at the very beginning, which is probably R and, no, the other way, and R. This is in the middle, this is probably now. Then 3 at the end, yeah, where are you? And I can transform also my test data. So now I have two sparse matrices, one representing my training data, one representing my test data. And I can train now a linear classifier on it, for example. Linear classifiers are great for text data. I call the fit method on the training data, call the score method on training data. See, I get 88% accurate. If I look at the test data, I'm not entirely as good, but looks reasonably well. So 83.6% accuracy on a test set. Now I'm going to introspect my model a little bit. So here, I look at the coefficients of the linear model that are largest and smallest, so the ones that are absolute large. And I take the 25 largest and smallest, call them negative and positive coefficients, and then I plot them. And maybe you can see them. So the red ones are ones that are indicative of not being an insult, and there's like better, love, fans, where, having great, well, blind, kind, Obama. And then there's the ones that are indicative of being an insult. Idiot, dumb, moron, loser, stupid, not gonna read the others. It's interesting, sometimes you get mother, that's also good. Yeah, oh, if you do, okay, I'm going to do 2 grams in a second, then you get mother definitely. 5 grams, yeah. Okay, so we can, we learned we can do, if we have a transformer and a classifier, we can pack them together in a pipeline, and then we have a lot less code to write. So let's do this here. So I make a pipeline out of the count vectorizer and the SVM. And if I fit and score it, I get the exact same results. It's the same as I did before. And so now that I have this pipeline, I can do grid search with it. And the first thing we can grid search is over the parameter C. So here, at the classifier, so I called the first step classifier, or the second step classifier, the SVM. At the classifier C, I do a logarithmic grid. And if I fit it, which will find the best parameter setting, then I score it, and I get slightly better. Actually, I just realized I didn't have the, did I? Oh, no, okay, never mind. Okay, so I get slightly better. I already adjusted the C above, I think. So here's now an example where we search over both steps. So I adjust the C of the classifier and the n-gram range, which is like, what is the lowest number of words I look at and the largest number. So 1, means I look only at single words. 1, 2 means I look at single words and neighboring pair of words, like how often do they appear. 1, 3 means I look at single words, pairs of 2 words, pairs of 3 words. 2, 3 means I look at pairs and triples, and so on. And I think I'm going to remove these in the interest of time and run it. I don't. So there was a question?
Let's say you wanted to do a cross-validation over, say, stemmers and LTK. Is there any way of using something outside of Scikit-learn pipeline?
You can give the count vectorizer analyzers and tokenizers. So you can give it a stemmer from an LTK, for example. And so you can do something like and then you give it here a different stemmer one. And these are like the functions that in the format that the count vectorizer expect them to be.
Only if it's supported. Like, you can only do these things supported. Is that somehow?
No, So analyzer can get a callable that will, yeah, I would have to look at the documentation. It allows I think the analyzer allows you to pre-process the tokens. And so you could give it a callable that maps a string to a token. And so you can use, as this callable, any function that you can define anyway, right? So let's say I have a Porter stemmer from NLTK, and I write a lambda that has the right input-output so that convectorizer accepts it. And this is one of the functions. And this is a function that uses the right format that convectorizer expects with another stemmer. Okay. This worked. And it says, the cross-validation said doing 1 and 2 grams is better. But this is not the. Sorry. I actually want to show you the thing. But maybe never mind. You can do this yourself. Visualize the coefficients of this. Very interesting. So, okay, we still have like 15 minutes. So the next thing I want to talk about is feature unions, which is yet another tool to build more complex pipelines. And for example, if you want to extract many different features inside a pipeline, then you can use feature unions. Or if you want to, if you have a pandas data frame with some heterogeneous data and you want to pre-process each column of the data frame in some different way, in a way that uses the training data somehow. So what feature union does is basically it takes in like your data, then gives the same data to a set of transformers and concatenates their output with horizontally. So you can add many features together. And for example, wait. This is the same notebook. Okay, so here I use like another text data set. Actually, I don't know why I picked here different text data sets, but okay, it's just a different, it's a text classification data set. But let's say I don't only want to build character n-grams and do this convectorizer on word level, on word n-grams and do the convectorizer on word level, but I also want to do that on characters. So I want to look at tuples and neighboring pairs of characters. This would be convectorizer with analyzer equal to char. This is maybe more robust against bad spelling and so on. So now you can do make union of these two different convectorizers that both build their own vocabulary and transform the data. And then if you call transform on the union, then the two outputs will be concatenated. Then we can make it even more complex and say make pipeline with this character and word token word vectorizer and with a linear SVM. And then because otherwise it would be too easy, I do a grid search over the parameter C. And so this is now fairly complex pipeline where you start with your text, you build a vectorized representation using either words or characters, concatenate them, put them in a linear SVM, and train. And then I do grid search over everything. Okay, this takes a little bit, apparently. And if you want, you can go even a step further, and you can grid search again over the parameters of these vectorizers say what range of characters and words you want to look at. And if you want to do that, you have to build a param grid like this. So we know that for the pipeline, you have to say the name of the pipeline, double underscore, name of the parameter. So for linear SVC, that was a second step. We just do linear SVC, double underscore C. So now we also have this feature union with 2 steps in the feature union. So the step is called feature union. And inside the feature union, we have 2 count vectorizers. So there's count vectorizer 1 and count vectorizer 2. So this is the first and this is the second. These are the names inside the feature union. And then I want to adjust the parameter called ngram. So here I have now 2 levels of underscores. So in the pipeline, I want to look at the feature union. In the feature union, I want to look at the first count vectorizer. And on this, I want to adjust the ngrams. And so this can get arbitrarily long if you nest things. Don't nest things arbitrarily deep, but it's pretty useful to build these more complex models. Questions? Okay. Let me check. Okay, I don't think we have time to go over all of the rest. I think I have like 20 more slides maybe. Do you want to? Okay, sorry. Give me a second. I want to see what I have in this deck. Do you want to talk about out-of-core learning, randomized hyperparameter search, or model complexity, or scoring functions? Out of core? Okay. Out of core. Okay. Actually. Okay, out of core learning. So what I mean by out of core learning is learning with data that is so big that it doesn't fit into your RAM, but it still either fits on your hard drive or you can stream it in over the network. So we're still talking single machine, but bigger than your RAM. The first thing I want to say about this, I had actually a half-hour talk about it at PyGotham, is don't do it. Just get a bigger machine. This thing here is it's a fairly old EC2 machine. It has 256 gigabyte of RAM. It costs like $5 or $7 an hour or something. I don't work for Amazon anymore, but still, get one of these machines. So who has more than 560 gigabyte of data? Okay, 5 people, yeah. Okay, so you can do out of core. The rest, just get this machine. Seriously, it's not worth the effort doing anything else. You can just open Jupyter Hub, your Jupyter thing, do your pandas, do your Scikit-learn. It's much easier than trying to do any out of core or any Spark stuff. If you have a couple of terabytes, it's a different story. Yeah, so this is my old laptop. It has 4 gigabyte of RAM. Actually, this is not my old laptop. This is my new laptop. It has 8 gigabyte of RAM. So this houses then 2 million data points with 1,000 features, which is a lot. And the EC2 machine houses like 68 million data points with 1,000 features dense. This is really a lot of data, so just get a bigger machine. Okay, but so if you have terabytes of data, then you can use the out-of-core capabilities in Scikit-learn. And there's a bunch of algorithms that support this now. So there's all the SGD classifier, SGD regressor, perceptron, passive-aggressive, and so on. These are like the SGD classifier derivatives, the naive Bayes algorithms, mini-batch k-means, Birch incremental PCA. Birch is a clustering method. And mini-batch dictionary learning, which is like a sparse coding algorithm. Oh, we also just, in a new release, it's also in standard scalar, min-max scalar, and robust scalar, so the preprocessing methods. And so I'm going to show you how you can use this. So here, I simulate that I have a lot of data by dumping my This is Python 3. By loading the, I'm sorry. What? Apparently I haven't run this in Python 3 yet. That makes me sad. Oh, yes. Thank you, anonymous voice from there. OK, so I just write out my digits data set in 10 batches. So I want each of my chunks that I process to be as large as possible. So basically, as large as my RAM minus what my operating system takes up. So I wrote all these files into Pickle. You could also use like CSV file and use the pandas chunk loader. It's also a nice thing. And I use the SGD classifier. And I want to classify the data that's in these batches. So what I do is I load each of these batches. And so there's 10 of them. And then I call the partial. Call the partial fit method on each. Sorry about this. Yeah. Why do things get more complicated over time? Yeah, so, and I call partial fit. So the difference between fit and partial fit is basically just, if you call fit on a model, it'll forget anything it ever saw before. If you call partial fit, it'll try to improve the model, and it assumes that each call to partial fit gives it a new chunk of the data. So you can do this in a streaming setting, so you can stream through data that comes in over the wire, or you can iterate over batches that you stored on disk that don't fit into RAM. The only difference is that if you do classification, you have to tell it what the classes are, so it can allocate the memory for all the classes beforehand. So otherwise, it has the same interface as fit. You give it the X batch and the Y batch. And so here, I iterate over the data once. For many of the algorithms, it's a good idea to iterate over the data multiple times. So I can do for j in range 10. Then, so this way, it will iterate over the data 10 times. And for each of the 10 times, it'll go through the 9 batches. And then here, I load the last batch, the 10th batch, which is called 09. Yeah. OK, never mind. I probably overwrote. OK. So yeah. So now I iterated over the first 9 batches a couple of times, and then I trained it. Then I tested it on the last batch. And I said, so otherwise, it's good. Like using pandas chunk loader allows you to read over chunks in CSV files, because why wouldn't you store your terabytes of data in a CSV file? That happens, unfortunately, too often. So it's unfortunately, at the moment, not possible to build out-of-core pipelines. We work on it, but it's not done yet. But there are some other cool things that you can do, which I like to call stateless transformers. So the thing is, if you want to use some feature extraction or preprocessing, you would actually have to iterate over the data twice. So first to build your feature extraction or preprocessing, and then again to build your classifier. If your data comes in over the wire and you don't know, and it never ends, that's not possible. A slight trick to get around this and to do something more interesting is to work with stateless transformers. That basically, they don't depend on the data. So you transform the data in a way that's independent of the training data. That's not really machine learning, but it's very helpful. And so you can, for example, use a normalizer for scaling your data that just makes every vector unit length. You can do the hashing vectorizer. It's an alternative to a bag of words that doesn't need to Actually, I'm going to explain it in the next slide. OK. It doesn't need to store the dictionary. So it's a way to do online learning on text, or the RBF sampler, which is a way to do kernel approximation, which allows you to do kernel SVMs on infinite number of data points. So these are cool things. I'm going to go through the hashing vectorizer quickly and the kernel approximation quickly, and then we can stop for questions. So I just explained the bag-of-word representation. You have your string, you tokenize it, you build the vocabulary, you do a sparse matrix encoding. Critical step, you build a vocabulary. You need to have all documents, and you need to store the vocabulary in RAM. So it doesn't work in a streaming setting. If your data is very big, you might not be able to store your vocabulary in RAM. So bad idea. The hashing trick is an alternative to doing this. The first step is the same. You do the tokenization. But then you just hash the token. So you take the token as a string, like here, this is how you get ants, and you hash this we use a murmur hash function, which is like a non-cryptographic hash. And you then modulo the hash with some large number. So you have like an upper limit to what your hash can be. I think we do 10 to the 20. So you get a number between 0 and 10 to the 20 for each word. And then you use this number that you get. So let's say for this, so I actually ran it, I think. For this, you get the number 832,412. And for is, you get, well, a different number. And you use these as index into your sparse matrix. And you count how often each of these numbers appear. So if you see this, you look at the point 832,412 and add one entry. If you see this again, you add it again. And this way, you don't have to have a vocabulary. And you can just do this in an online fashion. There's two drawbacks. Only one of them is an actual drawback. First is, you now have, if you do the coefficient vector and you want to see what do these coefficients mean, there is no way basically to invert the hash. So before we had, on the insults, we had this bar plot where we said, well, if someone tells you you're an idiot, then he probably insults you. You can't do that. So then, because you don't know what the words were, you only have the hashed value. So that would say, like, some number below 10 to the 20, which will not be very semantic for you. The other sort of issue is that you can have collisions. So two words that are not actually the same could hash to the same string, because you said, oh, there can only be 10 to the 20 many different tokens. 10 to the 20. So first, 10 to the 20 is a very large number. Second, most words are very, very rare, and they don't matter for your task. So if two words collide, it's very likely that they don't matter, and so you don't care. And there's been a lot of empirical evaluation, and basically accuracy doesn't go down if your space is big enough. It's very unlikely that, like, I don't know, idiot and great will hash to the same value. It's just not going to happen, because the chance of that is 10 to the 40 or something. So don't worry about it. You lose the interpretability of your coefficients, but otherwise hashing trick is great.
What is the benefit of using the hashing trick?
Oh, the benefit is you don't have to store a vocabulary. So you don't have to have the RAM to store all possible words. And you can do it in a streaming fashion. So you don't have to go see your whole data. If you, let's say you do this on Twitter, and you get Twitter feeds in and in. You don't know what words there will be tomorrow. And so you can't actually build a vocabulary. If you do the conf vectorizer approach, you need to know all the words in advance. Here, you don't need to know all the words in advance. Oh. Yeah, I think I'm going to skip this. There's more notebooks if you want. But this is just doing the same thing as before with the insults, only that in the loop, I do hashing vectorizer.transform to transform the data. There's no fit on the hashing vectorizer because it's stateless. And you can you can use the output of the hashing vectorizer to fit the linear model. OK, I think we'll stop here. Any more questions?